Hi, in this video we are going to talk about AVL trees and going to see a little illustration of how these rotations work. So let's get started. Let's suppose the situation we have a tree-like structure like this with the root node 32, left subtree and right subtree and so on. And for example, we would like to insert the 12. Okay, how do we insert? We start at the root node. The 12 is smaller than 32, we go to the left. The 12 is greater than 10, we go to the right. The 12 is smaller than 19, we go to the left. But because the 16 doesn't have any left child, we are going to insert it here. Okay. And we have been discussing that what's the difference between balanced trees and standard binary search trees. That for balanced trees we have to check on every insertion whether the tree is balanced or not. So let's calculate the height parameters. Okay, it's important that to be able to write the algorithm for calculating the height, we consider null pointers, so when a node have no left child, for example, to be of height -1. This is what we have been discussing in the previous video, but it's quite important, so that's why I repeat myself. Okay, so for example this 12 has the height parameter 0 because this is a leaf node. Then the 16 is going to have the height parameter 1 because this is the formula. We have to calculate the height with the maximum left child height, right child height, and we have to increment it by 1. So the 16 doesn't have any right child, and basically the 19 doesn't have any right child, so it is a null, but the null has a height parameter -1. And okay, we come to the conclusion that the left subtree of the 19 has a height parameter 1, and the right subtree has a height parameter -1. The difference between the two of them is equal to 2. It is greater than 1, so we have to make some rotations. Okay, so after the right rotation, it's going to be the new binary search tree. We have the 16, and the left child of 16 is going to be the 12, the right child of 16 is going to be the 19. It is a valid binary tree again, but in this case it is much more balanced. Okay, so let's calculate the height parameters. All the leaf nodes have a height parameter 0, and then we have to use this recursive formula. So that's why the node 16 is going to have the height parameter 1. Then we can calculate the height parameter with the help of recursion. And after the rotation, it is a valid balanced tree. The height of any left and right subtree do not differ more than 1. So no further rotations are needed. Okay, so let's prove it. For example, this is the left subtree and right subtree of the node 16. Okay, both of them have the height parameter 0. We don't have to rotate. What about this one? We have the right subtree and the left subtree for the node 10. We have the height parameter 0 and 1. They do not differ more than 1, so we don't have to rotate them. Okay, what about the left subtree and the right subtree of the root node? We have the height parameters 2 and 1. They do not differ more than 1, so we come to the conclusion that this is a balanced binary tree. We don't have to make further rotations. Okay, let's consider another example. We would like to create a balanced tree out of a sorted array. We have the 10, 20, 30, 40, 50 and 60. We have been talking about in the first lecture that if we construct a binary search tree out of a sorted array, then we are going to end up with a linked list with the ortho and linear time complexities, and we don't want that. So that's why this AVL tree and red-black tree came to be, to enable this data structure to preserve the ortho logarithmic time complexity. So let's consider this example and take a closer look at how AVL trees work. Okay, the 10 is the first item, so we don't have to consider anything. Then the 20 is going to be greater than 10, so it's going to be the right child of the 10. Okay, it's going to be a balanced tree, but let's check it. We have to check starting from the node we have inserted. It doesn't have any left or right children, so basically it is a leaf node. That's why the height parameter is going to be 0 for the node 20. Okay, so basically this 20 doesn't have any left or right children. there are null pointers, and the null pointers' height parameters are -1. The left subtree has a height parameter -1 because of this, and the right subtree height parameter is -1. Okay, the difference doesn't exceed 1. What about the root node? It has a left subtree, basically a null pointer with the height parameter -1, and the right subtree with a single node, the 20. The 20 is a leaf node with the height parameter 0. The left null pointer has a height parameter -1. The difference between 0 and -1 doesn't exceed 1. So let's continue with the insertion. 30 is greater than 20. 30 is greater than 20, so it's going to be the right child of 20. Let's check whether the AVL properties has been violated or not. What about the 30? It doesn't have any children, so the left child is a null pointer, the right child is a null pointer. This node is basically balanced. What about the 20? It has a null left child with height parameter -1, and the right subtree with a single node 30. Because it is a leaf node, its height parameter is 0. The difference doesn't exceed 1, so that's why this subtree starting at the node 20 is going to be balanced. What about the root node? The root node left child is a null pointer with the height parameter -1, and the left subtree is going to have the height parameter 1. Okay, because the height parameter of the leaf node is 0, and the 20 has a right child is 30 with the height parameter 0, so we just have to increment its height parameter to get the node 20 height parameter. 0 plus 1 is 1, so that's why the root node left child has a height parameter -1 and the right child height parameter 1. The difference between the height parameters is greater than 1, so we have to make rotations. And this is basically the doubly right heavy situation, so we have to make a left rotation on the root node, which is the node 10. Okay, this is going to be the solution. We would like to continue with our insertion, so let's insert 40. 40 is greater than 20, so we go to the right. 40 is greater than 30, so we insert it to be the right child of the 30. Let's check whether the AVL properties are violated or not. Okay, the node 40 is a leaf node, so basically it is balanced. What about the 30? It has a left child null pointer with -1 height parameter and the right child node 40 with height parameter 0. The difference doesn't exceed 1, so this subtree is considered to be balanced. We keep going to the root. What about the root node? The root node left subtree has a single node, the node 10. It has a height parameter 0 because this is a leaf node. What about the right subtree? It has a height parameter 1. The difference between 0 and 1 does not exceed 1, so it is a balanced binary tree. Let's keep on inserting items. 50 is greater than the root node, so we go to the right. 50 is greater than 30, so we go to the right. 50 is greater than 40, so we insert it to be the right child of 40. Let's check the AVL properties and the height parameters. The 50 is a leaf node, so it is balanced. The 40 has a left child with -1 and the right child with 0 height parameter. This subtree is balanced. Keep going in the direction of the root node. This 30 has a left subtree with the null pointer basically, with height parameter -1, and the right subtree starting with the node 40 with the height parameter 1. The difference between the height parameters is greater than 1, so we have to make a rotation. This is basically the doubly right heavy situation, so we just have to rotate this node 30 to the left. Okay. Let's keep on inserting items. What about 60? 60 is greater than 20, 60 is greater than 40, 60 is greater than 50, so it's going to be the right child of 50. Let's check the height parameters. Okay, this is a leaf node, so by definition it is balanced. The 50 has a left child null and the right child 60 with -1 and 0 height parameter. This subtree starting with the 50 node is balanced. What about the 40? It has a left subtree with a single node 30 with height parameter 0 and a right subtree with height parameter 1. This subtree is okay, it is balanced. Keep going in the direction of the root node. What about the root node? The root node has a left subtree 10 with the height parameter 0 and the right subtree with the height parameter 2. Okay, they differ more than 1, so we have to make a rotation on the root node. So we have to rotate the root node to the left, and it's going to be the solution. Why is it good? Because as you can see, it's going to be a balanced tree. We keep inserting items from a sorted array, but unlike binary search trees, because of the rotations, it's going to be balanced. Why is it good? Because the logarithmic running time is going to be preserved, and that's why it's going to be faster than looking up for an item in a linked list. Okay, so that's all about this example. Thanks for watching.